Hello and welcome. In this video series that we start now, we will talk about the wind and the wind behavior itself. And what we are discussing in the first video here is why air is moving, why we have wind at all. And we also will discuss how much power and energy is there in this moving air. First, we will have a look on the global wind system, and therefore we have a bit a closer approach to the globe. And first I try to draw here the equator that is more or less in this area, and then we have here the North Pole in this area. And what we all know is that the air is heating up at the equator much more than at the pole, and that is due to the fact that we have the sun shining here much stronger than here to the poles. And when then the air is heating up faster at the equator, the density is decreasing, and as a consequence, air is moving upwards. And the opposite we can observe at the pole, and there the air is cold, therefore the density is high and air is falling down. That means here we observe something like that. And now we could imagine that as a consequence, when the air is rising at the equator and therefore is missing there, we have an airflow from the poles downwards south, rising then at the equator, going high and then going backwards to the pole in this direction. But in reality we observe something different, even that seems to be logical. So when the hot air is rising here at the equator, it is already cooling down here, and by this cooling down process it is getting denser, and we observe that the air already here is falling down. And then we have here a closed loop, and that is typically around a latitude of 30 degrees. And something similar we observe at a latitude of 60 degrees. There, this cold air coming from the North Pole is already heating up and then rising here around 30 degrees. And then we have a closed loop here. So we have a second loop. And then it's not the last one, because when the air is falling down here, it induces air from this side going also down. And then this air is going into this direction. And the same is the rising air here coming from North Pole at 60 degrees, inducing also air from here. And we get here a next closed loop here in this direction. When we now have a closer look to all that, for example, the air going here northwards from 30 degrees latitude, we do never observe a wind directly going to the north. And that is due to the fact that our globe is rotating, and that's the Coriolis force. That means our globe is rotating from west towards east, and that means when the wind is just moving north from an observer out of our globe, it also has this rotational speed here, has also a movement from west towards east, and therefore finally the velocity component is like that. When we now observe somebody who is standing here, he or she has also a rotational speed in this direction, but that is slower than someone who is standing at 30 degrees, or even the fastest would be the one who is standing at the equator. And someone who is moving here at 60 degrees gets then a wind coming more from the southwest. And that means we have winds here in this area by Coriolis force moving more into this direction. And something similar we observe when a wind should go from 30 degrees southwards. Also there we have this component in direction of the movement of the globe. But now someone who is standing at the equator and rotating much faster with the equator and so also faster like this eastwards velocity component of the wind is noticing more wind coming more from the east, and therefore we have here winds going in this direction. And the same we see close to the poles. There we also have winds moving like that. Now the same we also would observe on the southern hemisphere, but that we are not painting now here. That is exactly the same, just mirrored at the south. But what I would like to mention is it's not the complete air that is moving in those three loops. We have also a part of the air that is not going down here, but really following here this movement that I originally had been drawing. And when we have that here from the equator, but now high in the air, then the Coriolis graph force is getting stronger and really orienting towards the east. Additionally, we have here this air is colder than the one coming here from the south. And as the colder is denser and would like to go towards where the south one is going, we have also movements high in a few kilometers above the air going towards the east, and that you have a very high currents, and these are the so-called jet stream. And that is for nowadays wind turbine technology not of interest, because we don't have wind turbines reaching kilometers high. But maybe in future we also might be able to use winds of a few hundred kilometers per hour speed. Nowadays aircrafts are using them, for example. But let's continue with more local wind systems. So, for example, and the most dominating maybe we have on Earth is that typical sea-land circulation. And the reason is again sun. So when sun is rising in the morning, then the land is rising in temperature faster than the sea, the water is doing. As a consequence, air is less dense above the land and is rising, and then is taking air from seaside, and we have this wind coming from the sea towards the land. And then we close the cycle, and for sure we have several of those loops. When it's now getting night, we see the opposite. Now the water keeps the temperature longer than the land is doing. So the land is cooling down faster, and what we see then is air falling down above land and rising above the sea level and closing the loop like that. So now we have the opposite flow of air that is coming from the land and going towards the sea. But we have also other wind systems, local wind systems. As another example, we take and we stay at night, we have a look to these mountain valley circulations. So it is night, and as a consequence, we have here the surface of the mountains that is cooling down faster than the free atmosphere. And as a consequence, the air is going from the mountains towards the valleys. And that is at all parts of the mountain. And as a consequence, we have this airflow coming from the mountain towards the valley. Now it's the next day. So sun is rising, sun is heating up now here, the mountain areas. And as a consequence, air is getting less dense, is rising. And then we have these typical air movements from the valley towards the mountains, and we have the opposite flow of wind. These are only two examples of local air systems. Now we are more interested how much power and energy that is inside the wind, inside this moving air, that we could use then later with wind turbines. And what we all know from school, that is the kinetic energy that is just expressed as 1/2 times the mass of the air in this case times the velocity to the 2. And it should be our equation number 1. When we now would like to know the power that is in the wind, we need to derive the energy by the velocity, and we get then the power that is 1/2 times dm derived by t times the velocity to the square. And that we also can write equal 1/2 times the mass flow times the velocity to the 2. And this is our equation 2. What we now also can express is that when we have the velocity here that is crossing a certain circular area, that later could be the area that is covered by our rotor blades, that is the area A. And after a certain time, this circle has moved a certain distance, and that is then the distance S. Then we also can express our mass flow equivalent dm divided by dt, and that we can write also as the density rho times the volume of this cylinder, and divided by dt, and that we can write also as rho times the area A times the distance S divided by dt, and that we can then also write the constants rho and A times ds times dt, or divided by dt, and that is rho times A times, again, once more, the wind velocity v. That is our equation 3. And when we now insert this equation 3 into equation 2, then we get the power P is equivalent 1/2 times the air density times the area A times the velocity to the 3. And that is our equation 4. For the moment, it's absolutely okay when we consider the density of the air as 1.2 kilogram per cubic meter. In reality, the density also slightly depends on the temperature of the air, on the humidity. But for our first rough calculations, we can consider that as constant. When we have now a closer look to this formula, what is really exceptional is that the power depends on this velocity to the 3. When we compare that, for example, to solar energy, when we have the double irradiation of sun, we have more or less double the power a solar panel, for example, will produce. But in case of wind power, when we double the wind velocity, we have 8-fold the power. And that is something we need to learn and to handle with our wind turbines. We can take advantage, but it also causes some problems. And here I once more have plotted here this extreme increasing curve with the wind speed. And on the vertical, we see the specific power in kilowatt per square meter of rotor area, for example. And also when we go more in that area where we nowadays operate wind turbines between 0 and 30 meters per second, the behavior of this extremely increasing power remains. Quite interesting is when we look at nowadays wind turbines, for example, they reach their nominal power already at a wind speed something between 10 and 15 meters per second. And there we see how low that is in the specific power. Nevertheless, in the lecture later we will learn why it is meaningful to have exactly this nominal wind speed in this area. That is just an outlook for future lectures. And to end, I would like to discuss how much power and energy is really in this moving air. And we already have learned that the driving force for wind is the solar irradiation. And the solar radiation, the yearly solar radiation on Earth is 1.5 times 10 to the 18 kilowatt hours. And we assume that approximately 2% of this solar power is converted into wind. And that results in a theoretical mean power of 4 times 10 to the 12 kilowatt. And that is 100 times more than the installed nominal power of all power stations worldwide. But that is a very theoretical potential. When it's going more to a technical potential, and we assume, for example, only those parts of the atmosphere close to 80 meters above ground, where typically wind turbines are operating, and there we have an average wind speed of 4.6 meters per second around the globe. And when we then only take the better sites into consideration that have a wind speed class of 3 or higher, and all of those sites, because we cannot use all the sites, only 20% of that, we come to an annual energy that we are able to gain of 72 terawatt. And therefore, I need to say that that is almost corresponding to the annual energy demand of all the Earth. And when we only look to the electricity demand, that is 7 times more than the electricity demand. And with this outlook for the next video, where we will discuss how much of this power of the wind we are able to extract with a wind turbine, I would like to end here the first video. Thank you very much.